at how to also do with the Lagrange multiplier. So let's quickly start with the substitution. Constraint optimization by substitution by looking at the example. So let's consider a firm who faces with the production function. This is a production function, 12 output, that is Q. Q is the output. Q is equal to 12K raised to the power 0.5 and then L 0.5. Now, this is the output. Then the output is a function of capital and labor. We see that it is 12. 12 is constant. The K there represents capital. The 0.5 is the share of capital that goes into output.
I believe it's 0.4.
0.4, yes, 0.4. It's the share of capital that goes into output. And then the 0.4 at the labor side should also be the share of labor that goes into productivity. So, and then now, I think one should be 0.6. Let me confirm the equation. Because if you add them up, they're supposed to give you 1. You come and let's confirm the equation. Okay. I think it's fine. Let's move on. So this is the output level of the firm. So out of that, we have 0.5, we have 0.4 that go into as capital that goes into productivity, 0.4 as labor, the share of labor that also go into productivity. Now let's look at the budget or what the firm has in order to maximize profit. The firm can buy input, capital, and labor at the price per unit of 40 Ghana cedis, the 40 Ghana cedis of capital and 5 Ghana cedis of labor. Now, if the firm has a budget of 800 Ghana cedis, what combination of capital and labor should the firm use in order to maximize its possible output? So here we can clearly see that the firm has some amount of money, and this amount of money, the firm can spend some to buy capital and spend some to also buy labor. At the end, the combination of, we want to know at the end how much capital and labor that the firm can produce in order to maximize profit, given 800 Ghana cedis as its resources. So this is the question. Very interesting question. Let's try. Let me open empty so that we can solve it there. I want to copy this so that we can solve everything in the fresh page. Copy this. Then I'll go here and I'll stop sharing. Then I'll go to the bot. Yes. So give me a minute. Let me project the Please, can you all see the whiteboard?
Yes, sir.
Yes. That is the whiteboard. I want to paste this thing there. Yes. So we have it here. We are all going to solve it together. How to maximize the firm profit or the firm output. Okay. So if we have something like this, the first thing we should do is to look at to look at what we call the budget constraint, the budget constraint. And we see that from the question that the firm is having see, the firm is using capital and labor to produce a certain level of output, but the firm must buy the capital and labor at a certain amount of money. So the amount of capital and labor, if we are going to combine them together, it should give you how much the cost of capital and labor should be equal to how much resources the firm has. So first of all, what we are going to do is that let's look for what we call the budget constraint. And the budget constraint is the total resources that the firm is expected to spend on the 800 Ghana cedis. So we have something we call the total cost of the firm or the budget constraint. So the total cost here, what is the total cost of the firm? So the total cost of the firm is equal to the cost of capital multiplied by capital itself. Now, the cost of capital is what? Interest or rent. You can call it rent or interest. So the cost of capital. So because the firm is going to buy what? Capital. So we are going to look at the total cost of the firm. So we are going to look at the cost of capital. So the price that the firm is going to use on capital is called interest. So we are going to look at the interest. Then we multiply the interest, that is the cost of capital, by the capital itself, by the quantity of capital, K. Then we add it to the cost of labor. The cost of labor is wages. So we write the wages here. Then we multiply it by the labor itself. That is L. That is L.
Hello, Doc.
Yeah.
So I can see the board and even the breakages in the network.
Please, who else cannot see the board? Hello.
So I can now see it. It has vanished again. It has vanished again.
No, maybe it's your internet.
Even when you are speaking,
can other confirm whether you can see or not?
Yes, therefore, yeah, I can see. So
I can see at my end.
Yeah, so please kindly check your internet connectivity. So what we are looking at is the cost of capital, the total cost that the firm is going to incur in buying capital and labor. Now, if you multiply the interest by the capital itself, or the cost of the price of capital and the capital itself, it's going to give you how much it costs to buy a capital. So the total cost of capital is the RK. Then if you also want to know how much the firm is going to spend on labor, you are going to multiply the wages by the labor itself. That will give you how much the firm is going to spend on wages. So we have the cost of capital, that is RK, the cost of labor, that is WL. Now, if you want to know the total cost that the firm is going to incur, you are going to add them together. That is why we are adding the total cost of capital, the total cost of wages, and that will give you the total cost that the firm is going to incur. Now, from the question, we saw that the firm has a resources of 800 Ghana cedis. So that will be the amount of money that the firm is going to spend on. So the firm total cost will now be equal to 800. The total cost here represent the cost that the firm has to spend on the goods and services. So it's going to give you 800 So it's going to give you 800. So it's going to give you 800. Then 800 is equal to the how much the firm is going to spend on the cost of or the price of capital. The price of capital was given as 40 in the question. The price of capital is 40. So in place of the R, you put 40 there. You put 40 there. So 40K. The K is not given. That is why we are coming to find out. Plus the price of labor is what given there as 5. So plus 5L. Plus 5L. And this, let's call this equation 1. Let's call this equation 1. This is what we call the budget constraint. The budget constraint. And the budget constraint simply tells you that if you have a total cost of or a total amount of 800 Ghana cedi, you should be able to spend between capital and labor, such that at the end of everything, if you add the cost of capital to the cost of labor, it might give you the 800 Ghana cedis. It is constrained. It is being limited. Okay, so whatever you are going to spend on capital should be equal to the amount of resources that you have. So at the end of the working, if you multiply the capital you are going to get by 40 and multiply the labor you are going to get by 5, it should be giving you 800 Ghana cedis. So that is what we are coming to look at. Now, you also know that our problem was given as 8 output is equal to, this is what we are looking at, output is equal to 12K raised to the power 0.5, sorry, 0.4, 0.4, and then L 0.4, 0.4. Okay. So this is what we have. So we can call this one, okay. This one should have been our equation 1, but no problem. So we can call this one equation 2. We can call this one equation 2. Now, the next thing we are going to look at is now we are going to use a concept that you have used in principle called the equimagina principle. Equimagina principle. So what the equimagina principle says is that the ratio of capital to or the marginal product of capital to its price, or the ratio of marginal product of capital to its price must be equal to the ratio of marginal product of labor with its price. Okay, So what the Economics principle says that we are going to use the MPK formula. MPK is the marginal product of capital. The marginal product of capital over the price of capital. The price of capital must be equal to the marginal product of labor over the price of labor. Over the price of labor. So that is what we are going to use here. So you know this marginal product of capital, you differentiate your output with respect to capital, and then MPL is also you differentiate the labor, the output function in respect to labor. So let's differentiate. So the MPK is the same as the partial derivative of output with respect to partial derivative of capital. Okay, so that is what we have as the so we are going to differentiate the output. Where is the output? The output is this. Q is equal to 12K raised to the power 0.4, and then L raised to the power 0.4. That is why we are going to differentiate. That is why we are going to differentiate. So let's do the differentiation together using this. So Q, let me write it here boldly so that we can all see. It's equal to 12 is equal to 12 A 0.5 0.4 and then L 0.4 and 0.4. So this is why we are differentiating. So here we are going to differentiate with respect to capital and also differentiate with respect to labor. So let's do the differentiation together. So if we differentiate capital, what are we getting? We are going to multiply 0.4 by 12. So 0.5 by 12 will give you 4.8. So you are going to get 4.8. 4.8. Then you write the capital there. Remember, this is a multiplication. They all go together. Then you subtract 1 from 4. 1 from 4. If you subtract 1 from 4, we are going to get minus 0.6. Minus 0.6. 0.6. Okay. But remember that we are not touching the labor because labor is not our interest now. Then you bring your labor there, 0.4. 0.4. 0.4. So this is your differentiation with respect to capital. You also have to differentiate with respect to labor. You also have to differentiate with respect to labor. So let's differentiate with respect to labor. So differentiation with respect to labor, we are going to get MPL. MPL is equal to the partial derivative of output with respect to the partial derivative of capital. The partial derivative of labor, sorry. Labor. Now, again, the same function that we are going to differentiate with respect to our labor. So here, the same thing, we are going to multiply the labor aspect 0.4 by 12. 0.4 by 12, we are going to get 4.8. We are going to get 4.8. Then we write our capital. Remember, we are not differentiating the capital, so the capital remain the same. The capital remain the same, but we are differentiating in respect to labor. So you subtract 1 from 0.4, and that is going to give you negative 0.6. Negative 0.6. Okay. So we are able to differentiate with respect to capital. We are also able to differentiate with respect to labor. So what is the next step to do? You know that the Economics principle is that the MPK over PK and then MPL over PL. Now you have found our MPK, we have also found our MPL. So we are going to substitute MPK and MPL into the formula, the Economics principle formula. So that is what we are going to do next. So we are going to get MPK, what is 4.8, 4.8, and then we have K 0 to the power minus 0.6, minus 0.6, and then we have our L there, which is let me write this thing. I want all of it to enter there. So we have 4.8, and then we have K, and then 0.6, which is negative 0.6, and then we have L here, which is 0.4, which is 0.4. That's the MPK up there, and we divide this one by the price of capital. The price of capital was 40, so we divide here by 40, and this one must be equal to MPL. The MPL is, we have also differentiated that one. We have 4.8, 4.8, K 0.4, and then L minus 0.6. That is the MPL here. And then the price of labor was 5. So we'll write 5 here as well. Okay. Write 5. So the next step is to, now we have, I think we have a common numbers here. We have 0.4 here. We have 0.8, 0.8, 0.8. So we can divide both sides by 0.8, 0.8, so that we can cancel off the 0.8 off. So let's quickly do that. So we are going to divide here by 0.4. Sorry, 4.8, and here too by 4.8, so that the 4.8 can take off the 4.8. Please, are you following?
Yes.
Yeah. So that is the first step. We are dividing. So when we divide, they will go off. So what we are going to get now is K 0.6, and then L 0.4, and this is equal to K 0.4, 0.4, and then L minus 0.46. And then this one is divided by 40. And this is also divided by what? 5. Okay. Now let's do something here again. Now, what is the LCM, the lowest common factor among this? What is the LCM here?
40.
If you have 40 and 5, what is the common number there? 40. So we are going to multiply both sides by 40. So we are going to multiply here by 40 and also multiply here by 40. So that this 40 can cancel off this 40. And then this 5 here goes 1, and 5 here goes here 8. I hope that is clear. Okay, so that we can get our K minus 0.6, L 0.4, and this one is equal to K, 8. So when we divided 40 by 5, we are having 8. So it's going to be 8. It's going to be 8. Then our K will come 0.4. And then our L will come 0.6 minus. Okay. So this is what we have now. Now, our main aim is to find capital and labor. So we are trying to make things simple here by making sure that we can make either L or K the subject. Either L or K the subject. So we are going to do something interesting here. There are two methods of doing that. First of all, we want to make things simple. So what we are going to do is that we want to multiply. You see, we have minus 0.6 here. We have 0.4 here. So we are going to look for a factor that if we add them together, maybe we can take off the K can vanish or the L can vanish. Okay. So that at the end, we can get one of them to be standing alone. So what we are going to do is that we are going to multiply both sides by K raised to the power positive 0.6. And then L positive 0.6. So we are going to multiply this one by our K minus 0.6 and our L 0.4. And this one should be equal to our K 0.4 and our L and our L and our L minus 0.6. So we are multiplying this one by the bracket, the whole of this, and let's see what is going to happen. Now, law of indices, if we are multiplying a set of functions of variables and they are having the same base, you are going to add the exponent. You are going to add the exponent. So if you are going to multiply k raised to the power 0.6 to k raised to the power minus 0.6. So let me separate that one for you to understand so that the rest. So we have k raised to the power 0.6 multiplied by k raised to the power minus 0.6. Law of indices, because the bases are the same, you are going to add the exponent. So you are going to get k, that's 0.6 plus minus 0.6. So it's going to give you minus 0.6 minus 0.6. It means that this one is going to cancel this. You are going to get 0 here. So at the end, this k is going to vanish. So we are multiplying this one by this. The k is going to vanish because it's going to give you 0. Any number raised to the power 0 is 1. So it's 1, it gets a constant. Okay. Then let's move to, we'll multiply L. I'm doing it one by one. L 0.6. We are multiplying L 0.6 by L 0.4 for the first part, 0.4. Now we are adding them because the bases are the same. So we are going to get L 0.4 plus 0.6. That is going to give you 1. So it's going to give you L raised to the power 1, which is the same as L. Which is the same as L. So the whole of this one is going to give you L. If you multiply this one by this, we are going to get L here. Because this one with 10, 0 or 1, this one is going to give you our L. Now let's move to the second one. The second one is the same thing that we are going to do. The second one is going to be the same thing. We are going to use, we are going to get k 0.6 multiplied by this second one is k raised to the power 0.4. It's not minus 0.4. And that is going to give you, we are going to add the exponent 0.6 plus 0.4. And that is going to give us k raised to the power 1, which is the same as k. Which is the same as k. So at this part, we are going to get our k here. Now k is here. So k multiplied by L. So let's move to the L. Now the L2, we are going to get 0. Sorry, we are going to get our L 0.6 multiplied by L minus 0.4. And that is going to give you L 0.6 plus minus 0.4. Sorry, the L is minus 0.6. Sorry, 0.6. Because we are looking at this, the last one, minus 0.6. So it's going to be minus 0.6 L plus 0.6 L. And that is going to give you L raised to the power 0. So this one will cancel this off. So this is 0.6. This one will cancel 0.6 off. So this one is going to give you 1. So we are having the L here to be 1. So what are we getting at the end? On the first aspect, we're having only L. L was remaining. On the first, we have L here, which is equal to. On the second part, we have only 8k, because here was raised to the power 8. Sorry, here was 8. Here was 8. The first part here is 8. But when we multiply the k raised to the power 0.6 and l raised to the power 0.6, we have only k to be here, and the k is going to multiply by our 8. So we have our 8 raised to the power now k. So we can call this one any equation. Let's say equation 6. So we are able to simplify this one. Now the next one is to, we are going to substitute the k someone is, can you mute? Okay. Now that we have our L to be equal to 8k, now we can do something interesting again. Remember that our budget constraint was given at 800. 800 is what we did earlier on. 800 is equal to 40k plus 40k plus 5L plus 5L. Now we now know that L is equal to 8k. So in place, we are going to substitute L into the function so that we can get something like 800 is equal to 40k plus 5 into bracket 8k. 5 into bracket 8k. Okay. So if we do that, we multiply here. So here 40k, sorry, 40k. So if we do that, we are going to get our 800k.
Please come again on the substitution aspect.
Okay. So here I'm saying that, let me wrap this one up.
Sir,
Yes.
it means we are putting 6 into 1. Okay.
Yes. So we are putting equation 6 into 1. Equation 1 was the output, this our budget constraint. So we are going to substitute L, which is in this one. This is 5L. So wherever we see the L, we substitute 8k there. 8k there. So you rewrite it as 800. 800 is equal to 40k. The first aspect is 40k plus 5L plus 5L. But the L here is 8k. So open the bracket and put our 8k there. And put our 8k there. So that you can multiply this one out. So you are going to get 40k. And then plus, let's see, 5 multiplied by 8 is going to give you what? 40. So we are going to get 40k. 40k. So we have 40k. So we have 40k plus 40k. 40k plus 40k is going to give you 800 or 80k. So 800 is equal to 80K. So we can divide both sides. We want to find K. Divide both sides by K. What will K be? Eighty, sorry.
Sir, both
80.
are 80 okay.
We're going to get 10.
So we are going to get 10. Okay. So we have found the value of capital, that is K. Now, if you are able to find the value of capital to be K, you can easily find the value of labor. Who can tell me what to do to find the value of labor? The value of L.
80.
You substitute the labor into the capital.
Yes, so you substitute the L, the K into L. The L is equal to, we all saw that the L is equal to, this is the L.
10.
L is equal to
80.
The
8K. So if we have our K to be 10, then you get substituted there. It's going to be 80 or 8 multiplied by 10. And that will give us what? 80. 80. So we have found the value of capital and labor. So capital is equal to 10. And then labor is equal to 80. So it is telling you that with the amount of capital or the amount of money that the firm has, the firm is able to use 800 Ghana cedis to produce 10 units of capital and 80 units of labor, and that will maximize the firm profit. So these are the output that the firm is going to combine. These are the input that the firm is going to combine. So the firm needs 10 capital and 80 labor in order to maximize his or her output. Now it is telling you that if you put this 10 and 80 into the budget line or the budget constraint, you are supposed to get 800 Ghana cedis. Remember that we are saying that whatever the firm has as a resources, the firm should be able to adjust everything in the output, in buying the input. So you can verify that our 80, we have 800 to be equal to 80K, sorry, 40K plus our 5L. Now, how do we verify that the firm must adjust 800 on capital and labor? So you have to look at the individual total cost by, K. So multiply 40 by K. We have found K to be 10. So you are going to get 10 here. And you have also found that we've also found labor to be 80. 80. So if you multiply this one by this, you are going to get 400. And you are also multiplying this by this, you are going to get 400. So at the end, 800 is equal to what? 800. So that is what the firm, so that is your budget constraint. So given that the firm has a limited resources, the firm is able to use all the resources that is available to him to buy 10 capital and 80 labor, and he is able to maximize its level of output. So that answers the question of the combination of capital and labor that the firm needs to maximize output. So you can conclude that the firm needs 8 8 units of capital and 10 units of labor. Sorry, 10 units of capital and then 18 units of labor in order to maximize its output. Any concern? Okay, so let me go back to the slides. Let me go back to the slides and see what we are going to get there. Okay, so we are able to find all the solutions here. Okay. Well, so let's look at another example here. Let's look at another example. But this example, I think, what is the cheapest way of producing 18 units of output? So let's look at this example again. The example is that a firm operates with the production function. A firm to operate with the production function Q is equal to 0.8, sorry, 4 K raised to the power 0.6, L raised to the power 0.4, and buys input capital and labor at a price per unit of 40 and 15 respectively. What is the cheapest way of producing 600 units of output? 600 units of output. What is the cheapest way? Now, what this one is telling you is that you are giving the output level. Here, you are giving the output level. The output level here is going to give you our 600, because they are saying that what is the cheapest way of producing 800 units of output? So Q output here, which is a function of capital and labor, is being given to you. So it is left onto you to find our capital and labor that will meet our 600 Ghana or 600 unit. So again, we can copy this one and go back to our words. To see how to work this one out. So please, there will be a lot of examples, but we might not be able to adjust all the examples here. So you have to be also working hard on your own. A minute, let me go back to the board so that we can work this out. Okay. I'll move to the so I've moved to the word or the board so that we can work it together. I hope you can see the board. Can you see the board?
Yes, sir.
Okay. So this is the question that we are going to solve. A firm operates with the production function. That is this is the production function. To highlight it. Production function is given. This is the production function and buys input capital and labor at price. Capital is equal to 840, and then labor is equal to 15. So again, so here we are going to use the same approach as the minimizing how to find output, how to find our capital and labor. But here, take note that we're giving output. This is the output here. And then Q here represent our output. K is the input capital, and then L is our input labor. And then 0.6 here is the share of capital that goes into output. And then the share of labor that also goes into output. Now, once we are given our Q to be equal to 600, we can rewrite this one to be 600. I'm going to rewrite this to be 600. 600 is equal to 4K 0.6. And then L 0.4. 0.4. Now, here is straightforward. We are not going to stress ourselves much. We are just going straight to the point. Once we are given this one, we don't need to go through the other stress again. But we can go through the other stress by setting up, by putting out the total cost there. Then we differentiate with respect to each other and then go through with the first one. This is the second approach that we should use once we are given the output level. So what we are going to do here is that let's make L the subject from this. From here, we are going to make L the subject. Before that, let's divide both sides by 4 so that the 4 will go away. So we are going to divide here by 4. And we are also going to divide here by 4. So that this 4 will cancel this 4. This 4 will go to this place, 150. So we are now going to have 150. 150 is equal to our capital, 0.6, and our labor, 0.4. Our labor, 0.4. Now, The next thing we are going to do is that I said we are going to divide, we are going to find the value of capital. Sorry, let's make L or labor the subject, making the labor the subject. So let's divide both sides by labor, so capital. So here we are going to divide here by capital, that is K 0.6, and here to K 0.6. K 0.6. So that K 0.6 here will cancel K 0.6 here. So what is left is we have 150 over K 0.6 is equal to L 0.4. Now, what we need to do is that we need L to stand alone, not L raised to the power 0.4. Not L raised to the power 0.4. So we are going to take the square root of both sides by 0.4. Remember, if you have this, let's say 25 or 27, it is going to give you, if you are going to take off, it's going to give you 27 squared, so that you can cancel this one and cancel this one off. Okay. And again, if you have let's say 2 raised to power 2, and you want to convert this to sorry, if you have 1 over 2, it's the same as having the square root of 2. Having the square root of 2. So let's come to this place. This one, we are going to divide both sides by 1 over 4, so that we can take off the 1 over 4 here. So here, before we can take off the 1 over 4, we'll divide here by 1 over 4. 1 over 0.4, sorry. 0.4. And also divide here by 1 over 0.4. 1 over 0.4. So that this 0.4 here will cancel this 0.4. So that we can have our 150 over multiplied by 0.4, 150. Then divided by K 0.6 multiplied by, remember this 0.4 is affecting both sides, multiplied by 0.4, 1 over 0.4. And this one will equal to our L. So if this one cancels this one out, it's going to give you only L. So we have L here. Okay. Now the next one is that let's divide 1 by 0.4. 1 by 0.4 is going to give you 2.5. You can try it and see. So it's going to give you 2 raised to the power 2.5. And then we divide this one by K. Now, this K here is going to be 0.6 divided by 0.4. 0.6 divided by 0.4, that is going to give us 1.5. 1.5. And this one is equal to our L. This one is equal to our L. Now, we can pick our calculator and now put the value there. 150 raised to the power 2.5. 150 raised to the power 2.5. Is it going to give us 275 6 2755 2755 6 7.6 7.6, and this one is divided by our k raised to the power 1.5. Okay, so this is our value of L. This is our value of L. Now, the next thing we are going to do is that we know that our total cost of the total cost that we are going to find here. Remember that the total cost is going to give you the cost in terms of capital. So RK plus our WL. And that one is the cost of total cost of capital, or the total cost that the firm is going to incur. The price of capital was 40. So you have 40K. And then the cost of labor was 15. So we have 15L. 15L. So what we are going, when we are find the value of L, we are find the value of L here. The value of L is this. So we are going to substitute the value of L into the function here, just like we did the other time, or with the first one. So our total cost here is equal to 40K plus 5, and then remember that the 5 is in the bracket. The 5 in the bracket, we have to
15.
Okay,
15.
come again. Yeah, sure. 15. 15. We have 7, 5, 5, and then 6, 7.6, all divided by K 1.5. 1.5. Okay, so this is what we have. But I am going to rewrite this one nicely. You remember the inverse law of indices. The inverse law of indices. For example, if you have let's say y minus 2 is the same as 1 over y squared. Or if you also have let's say 1 over, or let me use 20 over k squared. You can rewrite this one as 20 raised, and then you bring the k here, but the 2 is going to be minus. This is the inverse law of indices. So this one you can send it, if you want to, this is a fraction. If you want to turn it to a linear form, you can send the 2 there, but the 2 become negative. And the law of division law, that is the division law. We are dividing, we can turn it to minus. So I'm going to apply that law here in this scenario. So with this k here, k to the power minus 0.5, k to the power 1.5, k to the power 1.5, I am going to change it. Let the k come here, and then I'll put minus there. So I'll just do the substitution here. So I am going to get this. Let me cancel this one so that I can get our k here minus 1.5. Minus 1.5. Okay. It's the same as dividing this one by k raised to the power 1.5. It's the same thing. This is the law of indices. So this is what we have. So this is what we have. Now the next thing is that we are now coming to find out the value of other capital. We are coming to find the value of capital or labor, where we are using the minimization term. How do we find the value of capital and labor? Now we are going to now differentiate this one with respect to capital or labor. So this is in terms of capital. This is capital here. We also have capital here. So we are going to differentiate the total cost. So we are going to differentiate the total cost. So this TC over the capital K is going to give us, if we differentiate this capital here, you are going to get 40. The capital will go away, you are going to get 40. Then we are going to differentiate, this capital is also here, right? Capital is here. So this one is the whole function. It's a whole function here. This one is the whole function. Capital is here. So we are going to differentiate capital. We multiply 1.5 minus 1.5 by the 15. 1.5 by the 15. We are going to get minus 22.5. 22.5. Then you open the bracket, you put 2, 7, 5, 5, 6, 7, 6, 7.6. Then here, you subtract 1 from the exponent. Subtract 1 from the exponent. You are going to get minus 2.5. Then you now equate it to 0. This is the first order condition. So anytime you are differentiating, you have to equate it to 0. So this is what we have. Now, if you are able to equate this one to 0, then what it means that we can open the bracket here. You can open the bracket here. You can open the bracket here. So let's try to see. So I will now have, now I want to send, this is minus. This is minus, right? I want to send the minus to the, okay, well, I can decide to multiply it first before I do that. Any way we want to do it. Sorry, this is a K. K is here. K is here. So any way we want to do it, that is fine. But what we can also do is that, I can say 40. I want to send the 40 to the equal sign. So I can write 40, 40, this 40. So let's send this whole thing to the equal sign. So that 40 will stand alone. So 40 is equal to, it now be positive. So 2 2.5, 0.5, and then 27, 55, 67.6. Then you close the bucket, and you put our key. Now, what I want to do here is that I want to send this one back to our initial one. So I can divide here by k raised to the power 2.5. You see that here it is negative. So if we are dropping it, it becomes positive. It's the same way we sent it back. So I can also write it this way. I can write this one this way. It's the same thing. Now, I want to make k the subject. If you want to make k the subject, what will you do? We are going to cross multiply. We are going to cross multiply. So this one multiplied by this, and this one will stand alone. And then number standing alone is over 1. So this one will multiply by this, this will multiply by this. So we are going to get, I hope you are cooperating. I'm going to clean the upper one so that we can write there. I hope you are also writing.
Yes.
Okay. So I'm going to cancel the upper one so that we can write there. Okay. So if we cross multiply, we are going to get 40k raised to the power 2.5 to be equal to our 22.5 or bracket 2 is it 27?
So it's 27556.
Okay, 2755
Say 7.6.
7.6.
67.6. Okay. Okay, this is what we have. So if we have this one, I want to make k the subject. I will divide here by 40. I'll also divide here by 40. So that this my 40 will cancel this 40. So my k 2.5 is going to be this. So first of all, you have to multiply this one by this before you divide it by 40. So if we do that, what are we going to get? If you have a calculator, you can start doing it.
But we are going to get 6 million.
Come again.
We are going to get 6,200,000 and two.
Guess call them one. 8. You call them one by one for me to write.
We are
One.
going to get 6200.
Can you check it again?
Okay.
So it's true.
6200271.
6200.
271.
Give me a minute, Anthony. Can anyone confirm that?
Yes, sir.
Confirm.
Okay. You said you are going to get what?
6200
Okay.
271
62
0
0 271.
Yes, doc.
Is that correct?
Yes, doc.
Okay. So again, let's try to also do this. So now we want to make K the sub. We want K to stand alone. If K is going to stand alone, what we are going to get is we are going to make sure that K is
Doc,
standing
please,
alone.
we didn't do
We'll
the
divide by
division.
the 40.
Come again.
We didn't
We'll
do the
divide by
division. And the 6200271 is there. Is when we multiply 22.5 by 27.
Let's do everything. Multiply everything and divide by 40.
Okay, that one you are going to get 155
155
006
0
.775.
point 8.
Is it?
0.78.
Okay, okay, so
Okay.
convert, yeah.
Yeah, 0.78. That's fine. Okay. So let's make K to stand alone. We are all this while we are trying to find the value of K. We are trying to find the value of K. So let's make K to stand alone. So K to stand alone. Remember, we are going to get the square root of 2.5. 2.5, then 155 006.78. Yes, also do this and see what we are going to get.
Set 984.3.
984.3. Please
Yeah.
check. Let's one confirm. Please, the two
We are going to get
Yes,
Yeah, right.
984.3.
Come again.
984.3.
How do you do this square root? It's not multiplying. No. The 2.5 is sitting on top of the square root.
My case, I got 98.986.80911.
You
I
see,
don't
if you
know.
take your,
Dog,
I'm
I
not sure you
have
are getting.
986.
I'm not sure what you are using in your computer, whether it's the right one.
Dog,
Uh-huh.
I have different view. I had 986.809.
Do you have your calculator with you?
Yes.
Yes, sir.
yes, dog. Dog, when I
So-
computed mine, I had 984.27. So when you
so
run it
what-
on, then that gives you 0.3.
984.3.
Yes, that is what I
I'm
also have.
comparing it to what
Hello,
comparing it
sir.
to what. Yeah.
Please, I had 119.16.
Yes, that is correct. 119.16268. Yes.
68.
Yes, 68.
Doc,
So teach them how to use it.
Okay.
It is on your smart computer calculator, the scientific one. So you can see here to show you how to use this one. I would have demonstrated it that if you go to your smart, you will see the scientific you will see something like this. You see something like this. Then they'll put either 2 here or 3. They'll put 3 or 2 there, and here is X, something like this. So when you go, you can change this one to 2.5 after submitting. Then you put the value there, inside there. Then you get the right answer. Okay, so it's going
So I
to
don't
give
get
you
you.
119.168. 168, yes. You can leave it this way. Okay. Now, our capital is now given. We know our capital. So what we don't know is our labor. Where is our labor? Our labor is, did we find it somewhere? Yes, this is our labor. Let me clean this and write. You see your labor very well. So this is our labor. And we find that our capital was, or our capital is K is equal to 119.16268. So we are going to substitute capital into the labor formula. So if we are substituting, our labor will now become L to be equal to 2,755,5,5,6,7.6 all over our capital K. Our capital K. But K is now 1 point. So we are going to get bracket 1, 1, 119, 119.16268. All this one raised to the power 1.5. So you can also compute this one and see what we are going to get. And that will give us our labor. Compute this and let me know the answer. Yes, who has gotten the answer? Hello, please. Are you doing it?
Yes, sir.
Okay.
Kevin, I had 211.845.
Yes. So you are going to get 211.844
5.
Okay, 5. So you got 7, 8. So you are right, 8, 5. Okay. So this is what we also have for labor. So you have the value of labor and you have the value of capital. Okay. So okay. So remember that the question was what is the cheapest, or when we say about something cheaper, we are talking about the minimum. So what is the minimum way of producing output of 600? The cheapest, we mean the minimum. And when we say the expensive, we mean the maximum. So the minimum way of producing output. So once we are able to find the output level of capital and labor, then we can also demonstrate whether the production function follows minimum or maximum by taking the second order derivatives. So we are going to differentiate it to the second time to see whether it is maximum or minimum. Remember that we did this things last semester, whether to determine whether the function is minimum or maximum, we use the second order derivatives. So where is our derivatives when we differentiated the total cost? So let me clean this. We know our capital and labor. We are able to find them. Capital and labor. So we are now coming to confirm whether the output, capital and labor that we have found are at the minimum level, or they are at the maximum level by taking the second derivatives. So the derivatives, the first derivative that we did, we had the first differentiation that we did. Yes, we had 40. We have the first derivative that we did. It was our D2DC over our decay was equal to 40 minus 22.5 and then bracket 27.557.6. Then k raised to the power minus 2.5. This is the first derivative that we did. Now we are going to look at the second derivative. It means that we are going to differentiate this one for the second time.
We equate it to 0.
Yes, we equate it to 0. Now, to determine whether our function or our production function is at minimum or maximum level, then we are going to differentiate this function for the second time. So we are going to get our DTC going to get our DTC TC squared over our DK squared. It's telling you that we are going to differentiate this one for the second time. Second time. Okay. And if we are going to differentiate ones for the second time, see what we are going to get. We are going to get we are going to see this one is constant, so this one will not be considered. If we differentiate it, we are going to get 0, but we are going to differentiate the whole of this again. So what we do is that we are going to multiply the minus 2.5 by 22.5. So we are going to get, if we multiply this one, this is minus, so minus minus become positive. So we can say that it is going to be 2.5 multiplied by 22.5 before we also multiply this one by 275567.6. Then K. So again here we are going to subtract here by 1, and that is going to give you minus 3.5. And we are going to see whether this is greater than 0. If it is greater than 0, then we are talking about minimum. But if it is less than 0, we are talking about maximum. Okay. Now, how do we confirm whether it is greater than 0 or it is less than 0? We know the value of K, right? We know the value of K. So we are going to substitute the value of K there. You substitute the value of K there. If you substitute the value of K there, then you will know, will now come to know whether the function is minimum or maximum. Because for this one, you cannot tell whether it is minimum or maximum, whether it is greater than 0 or less than 0, unless you substitute the value of K there. So if you substitute the value of K there, I'm not going to waste time here. You can do that yourself to confirm. If you substitute the value of K, the K was 2.11.8, sorry, 211.84478. That was the K. So in place of this,
the K was 119 point.
Okay, that was it. The K.
The K was 119.16268.
Okay, that's fine. So we substitute that K in there. So if you substitute the K in there, you will see that it will be, even with this, you can see that it will be greater than 0. If you substitute the K in there, K here, it's going to be greater than 0. And that also confirms that our function is minimal. Our function is minimum. And that is why in the question, they stated that, that is why in the question, they stated that what is the cheapest? So when we hear about cheapest, we hear about minimal, we are talking about the lowest point that the firm can produce with this. So the minimum cost that the firm is going to incur in producing the output. Okay, so that is the confirmation. So we confirm that the firm is minimizing its output. The firm is minimizing its output. So you can also confirm that. Remember, we said our output was 600. 600 is equal to K raised to the power 0.6, and then L raised to the power 0.4. You can also confirm this. There was a 4 there. Yes, constant 4. There was a 4 here. So if you want to know that whether the output level you have gotten for labor and capital are correct, you can substitute the value of capital, which is 119 point something there, and then you can also substitute labor there. You can also substitute labor there, which is 2.11 something there, into the main function, and you will observe that what you have in the right hand side will be equal to what you have in the left hand side. So you are expecting that when you substitute everything there, you are going to get 600 here. Here will be 600, and that will be also equal to 600. That will also prove that whatever total cost that the firm is going to use, the firm is going to use it to produce a minimum output of 600. So you can confirm that later on. Okay. And if you are able to confirm that, then we can go ahead to look at maybe the total cost that the firm is going to incur. The total cost that the firm is going to incur. The total cost that the firm is going to incur. Remember that the firm has a total cost or the budget constraint. The firm has a total cost function or the budget constraint that the firm has to meet. So remember that we said the total cost of the firm was equal to 40K plus 15L. So you can find the total cost of the firm. How much the firm incurred to produce 600 units of output. So the total costs can be C is equal to 40, but you know the value of K. The value of K is 11916. So let's leave it this way. Plus 15, and you also know the labor. Labor is 211.84. Let's leave it at 84. And this one will give you the total cost that the firm is going to incur in producing 600 units of output. So when you do this one, you are going to get 7944. So this is the total cost that the firm is going to incur in producing 600 units of output. 600 units of output. Okay.
Doc, please, the second derivative for TC, I had, when I did the calculation, I had 0.839.
Oh, you substituted the capital inside?
Yeah.
Okay. Was it positive or negative?
It was positive, and it raised to the power negative 3.5.
Yeah, so it's positive. So
Yeah.
once you had it to be positive, then it means it is greater than 0.
Yeah, so I had 0.84.
Yes, you are right. 0.84.
Okay.
So it's greater than 0. So you confirm that it's minimum.
Okay.
Yeah.
Thank you.
Okay. Okay. So then let's move on to the slides and see what is there. Okay. So we are able to go through this. So we are able to go through this, and we had this as well. Okay. Now, what we have done so far is using the substitution method. Using the substitution method. So we can now move on to look at the other method that we are going to look at. The other method is what we call the okay. So the other method that we are going to look at is what we call the Lagrange multiplier. The Lagrange multiplier. So this is a method that after someone who also tried to use other means to determine whether the firm can maximize its profit or not by following some key things. Now, with the constraint for you to use the Lagrange, so in exams or question or in anything, they can restrict you to any of them. They can ask you by using the Lagrange approach or by using the substituting method. Okay, so it's better we understand both aspects of it. So I'm going to run this through so that we'll go to the example and we'll practice the Lagrange using the Lagrange method. So with this, I'm just going to run through this so that we can go to the examples and work on the Lagrange approach. So if you are given two functions subject to the constraint, just like what we did earlier on, the output productivity, or the firm is going to produce output given a certain constraint. So a function of x and y with its constraint, with its constant constraint, k is a constant. Now we can find a new function L that can form by the equation 1. So equation 1, the one is that we can find a new function of the Lagrange multiplier by following three simple steps. The first step is that we are going to set the constraint equal to 0. We are going to set the constraint equal to 0. The constraint is the same as the baguette line or the baguette constraint. We are going to set it equal to 0. Then 2, we'll multiply it by the Lagrange multiplier. And then 3, we add the product to the optimal function. When we talk about the optimal function, it's the objective function. The objective function is the function that, or for example, when we look at the production function, the objective function was the output function. That's the objective function. And then we'll subject it to the constraint. The constraint was the total cost function. The total cost function. So this is how we are going to set the Lagrange. The L here represents the Lagrange. X is the output, the function of x. So we'll differentiate with respect to x. Y here is the input y. We differentiate with respect to y. And then the lambda here is the Lagrange multiplier. We also have to differentiate with respect to Lagrange multiplier. So it's going to be our objective function. Our objective function plus the Lagrange multiplier multiplied by our constraint. This is our constraint. So we are going to multiply the Lagrange multiplier. We are going to multiply the lambda by the constraint, and we add it to the function. Then we equate it to 1. Then when you are able to set, so this is how we set the Lagrange here. And there's 2 ways of setting the Lagrange. When you are given the constraint function, you can either convert the function to implicit function. So we can see that we have x. The function is g x y is equal to k. So what we are going to do is that I'm going to maintain our k. K can be a constant, any number, and then xy can be any function. So I want to say k here, then send the function into the other side. So I'm going to have 1 k minus g x y, and now equate this one to 0. Now equate this one to 0. You have to do this. You have to change it to implicit function before you can put it into the objective function or the multiplier. Okay, so when we see examples, you see how I'm talking about. So that is how we set the Lagrange. And then here you can either use a minus sign here or addition sign based on how you are making the constraint function. Now, once you are able to set the Lagrange, then here is the Lagrange function. We call this one the Lagrange function. And then the function itself is the original or the objective function that I spoke about. And then the gx is the constraint. Gx is the constraint. So this constraint is always set to 0. So that we can find the product of the Lagrange multiplier. So you can also differentiate the Lagrange multiplier and also equate it to what? 0. Okay. So when we get to example, we're going to illustrate all this. So when you are able to set the Lagrange, then another one is that we can find the critical value. What we mean by the critical value is that we can find the value of x, y, and lambda. Just like we did for capital and labor, we can find the value of capital, we can find the value of labor, and we can find the value of lambda by taking the first derivative with respect to each of them and equating them to 0, and we can use simultaneous equation to solve them. So we can find the value of x and y, and then we can equate them to 0, then use simultaneous equation to find the solutions. Now we have the necessary and sufficient condition. The necessary condition is used when we want to find the critical values. So we differentiate each value or each variable and we equate it to 0. Then we can be able to do as group item and substitution. Then we are able to find the value of x or y. Then the sufficient condition is when we want to find whether the function is either minimum or maximum. We use the sufficient condition. That is the second order derivatives. So with the necessary condition, we are talking about the first order derivative. And then the sufficient condition, we are talking about the second order conditions where we can differentiate it equal to the second order condition. If it is greater than 0, we say it's minimum. If it is less than 0, we say it is maximum. So this is what we are trying to say. This is the first order condition. We differentiate them with respect to, when you differentiate for the first time, you equate it to 0. But the sufficient condition is when you differentiate them the second time, then if it is greater than 0, then we say minimum. If it is less than 0, then we say it is maximum. Remember, if you see XX there, it means the second, you are differentiating it for the second time. But if you see LX alone, it means it's for the first differential. Speaking about this. Now, the necessary and the sufficient condition the necessary and the sufficient condition yes follow a certain trend or follow a certain condition or rule to make sure that whatever whatever output we are trying to maximize or minimize, it should be in the same lane. So another sufficient condition that we are going to use to ensure that the function is at the optimum when we view it from all directions, but not in the direction of the principal axis. We are saying that this is the second order derivative of the function x, the second order derivative of the function L, y. So if we multiply the two together and is greater than, you differentiate the cross differential of x and y squared. So if we differentiate this one and it is greater than the cross differential of x and y, then we are also saying that you are also meeting the condition of being maximum or minimum. So, or this one here, we are talking about the x, the LXX is the same as the second differential of x. And then the LYY is the same as the second differential of y. And then the LXY squared is the cross differential of x, the cross differential of x. So when you differentiate the x for the first time, then you differentiate the x respect to one y. That's the cross differential. So we'll come to that soon, and you also understand how we are going to do that. Okay, so this is just explaining it. Now, another important thing is that okay. So we also have sometimes the sufficient condition or the second order condition is not satisfied. That is, if the second order condition is giving you alternative signs, you differentiate the second order is less than 0, it's giving you greater than 0, is equal to 0. If it gives you the alternative signs, what are we going to do here? The function either exhibit minimum from one axis and maximum from the other axis. So it is very difficult for us to come out with a specific conclusion on that. On the other hand, we are saying that when the second order partial derivatives are on the same sign, which points to either minimum or maximum, but the second order condition is not satisfied, then in that case, we cannot conclude on a specific concept, whether it is minimum or maximum. What we are going to use here, we are the only any of these situations that we are going to, if we encounter any of this situation, then we are going to use the bordered Hessian condition for us to solve this problem if we have alternative signs. Now, what does the bordered Hessian do? The bordered Hessian is just another format that we are going to use to determine whether our function is minimum or maximum. Our function is minimum or maximum. Okay, so what we are going to do is that we follow a certain rule. The rule is that we are going to differentiate a function for the first time, the square and square it. So the g x squared is the first function. Then we multiply it by the second derivative of the other function. Then we subtract it from 2. We subtract it from 2 the third derivative of the g, and then the first derivative of y, and then we multiply all by the cross differential of x and y. Then we add it to the square of g, and then the cross differential of x and y. Now, if we do that and the value is greater than, if we do that and the value is greater than 0, then we have, if the value is less than 0, we have maximum. If the value is greater than 0, we have minimum. But if you have it to be equal to 0, we have inconclusive. So in case the sufficient condition is not giving you the right sign, it is giving you alternative signs, then you have to move on to the bordered Hessian condition. And the bordered Hessian condition will tell us whether it is minimum, maximum, or inconclusive. Okay. So we can now look at example now using the Lagrange approach. Using the Lagrange.
I think Dr. Network is not helping him. Madam Ellen, can you help us how you did the, how you calculated for the K, that is the 2.5 square root of 155006.
It's like the 2.5 should be the root. Okay. So it should not stand alone. When it stand alone, you get the answer wrong, but it should be a root. I don't know whether you get what I'm saying.
Please come back again. Like, I don't know.
I was saying that the 2.5 should be like a root. Okay. Like a root. But when the 2.5 is stand alone, you get the answer wrong.
Oh, okay. I
It should
have
be
the
like a square. It should be like a square. Like,
I have what the doctor was saying on the calculator, but how to put that function on the screen and to do the calculation, that's what I'm finding difficult.
So like as I said, the 2.5 should be raised. Should be raised on the square root. When you do it like normal 2.5, you get the answer wrong.
Okay, thank you.
Please, are we here?
Yes, Doc, we are here.
Okay. So we are going to use the Lagrange approach. So first of all, first step is to set the Lagrange. To set the Lagrange. How do we set it? You see that we are having a function of x and y, but we also have what we call the lambda. So first, we are going to have the Lagrange, which is a function of x1, x2, and then x2, and then lambda. So this is what we are going to have. Then second, we are going to use our objective function. This is our objective function, which was f of x. So we are going to write our 25. We are setting the Lagrange. This is 25. You write it full minus x1 squared minus x2 squared. Then we now add our Lagrange. So this is the constraint. So we are going to multiply the constraint by the Lagrange, or we are going to multiply the Lagrange by the constraint. Okay, but before we do that, we are going to change the function to implicit function. So 2x1 plus, sorry, x1, so 2x1 plus x2 is equal to 4. So I'm going to change this one. I want to maintain the 4. So I have 4. Yeah. I want to maintain the 4. And I will send all this across the equal sign. So I will have minus 2x1 minus x2. I am maintaining this. I want the 4 to be there, but I want all this one to come across the equal sign. Then I will now equate it to 0. So this is what we are going to use to multiply with the lambda. So any function we are given and we are asked to set the Lagrange, that is how we are going to set it. Okay. Now, another way to also do is that once you are maintaining, sending the rest equal to, here is going to be minus. So minus lambda. Then you now multiply this one by 4. Sorry. So I said there's 2 ways to do that. If you have 2x1 plus 2 plus x2 to be equal to 0. Sorry, equal to 4. What you can do again is that you can maintain this one and send the 4 across. So if we do that, we are going to get 2x1 plus x2 minus 4. Minus 4. Simple. So just maintain this one and you bring the 4 across the equal sign. Send the 4 across the equal sign. So let's use this one. Let's use this one. Then you see how we are going to do it. So we are going to now multiply that one by our multiplier, our Lagrange multiplier. That is, we are now going to get 2x 2x1 plus x2 minus 4. And that is what we have. So setting the Lagrange is very, very important. Any question that you are given in this form and you are asked to use the Lagrange approach, you have to set the Lagrange first. This one. You have to set the Lagrange first. So it is very, very paramount for all of you to know how to set the Lagrange. Because any question that is going to come is going to be either Lagrange, using the Lagrange method or substitution method. And you have to know how to set the Lagrange very well. You have to know how to set the Lagrange very well. This is how we set the Lagrange. Okay. Now, if you are able to set the Lagrange, then we'll now differentiate this one with respect to x. So I can say x, if we see Lx, x1, it is telling you that I am going to differentiate x or L with respect to x. So I'm going to differentiate this one with respect to x. It's the same thing. So if we differentiate, let's differentiate that one. We are differentiating the whole of this wherever we see x1. So differentiate this x1 here. So we are going to get minus 2x1. Here is x2. We are not interested here. Then we have x1 here. We have 2x1. But the lambda is multiplying this. The lambda is multiplying the 2. So it's going to give you minus 2x lambda. Minus 2x lambda. So if you are differentiating respect to x1 there, the x1 will vanish. Okay. The x1 will vanish. What is remaining is minus 2 lambda. Minus 2 lambda. Minus 2 lambda. And this is equal to 0. This is equal to 0. So we call this one equation. Let's call this one equation 1. Then we'll now come and do.
Sir, please, can you come back?
Yes.
Come again.
Come again.
On the differentiation.
Okay, let's do the second one. You will get it. The second one, we are going to have x2. We differentiate the x2. It's the same as the L over the x2. So here we are going to differentiate with respect to x2. And the x2 is here. This is x2. One is x2. So if we differentiate this one, we are going to get minus 2. Because it is going to multiply the x1 to x2. Minus 2x2. Then you come and differentiate x2. This is x2 again. X2 is here. But this x2 is being multiplied. The lambda is multiplying inside. So we are going to get something like minus x2 lambda. Because lambda is multiplying inside. This is multiplying inside here. So if we are differentiating x, the x is going to vanish. What is left is only lambda. So we are going to have only lambda. And you now equate this one to 0. You now equate it to 0. Then you now differentiate respect to our lambda. We are now differentiating respect to our lambda. If we differentiate respect to our lambda, so this is equation 2. So we are now differentiating our dl over respect to our lambda. So that is lambda. So the lambda is here. The lambda is here. So the lambda is going to multiply 2x plus 2x1 plus x2 minus 4. So there's going to be lambda here. There's going to be lambda here. There's going to be lambda here. So if we are differentiating respect to lambda, all the lambdas will go. So it's going to remain the same function. So we are going to get the same function as 2x1 plus x2 and minus 4. And this is equal to 0. And you can rewrite this one as our 2x1 plus our x2 to be equal to 4. We are just selling this 4 across the equation 3. Then let's do something on the derivative that we have done. You see the first one here, we have it, it's equal to 0. Okay. And then also this one, we also have it to be equal to 0. So we call it equation 1 and equation 2 again. Now what are we going to do with this equation? So let me rewrite this equation very well for you to see. From here, we have minus 2x1 plus 2 lambda to be equal to 0. And we also have minus 2x2 plus minus lambda, sorry, be minus lambda to be equal to 0. These two equations, let's look at these two equations critically. You see, when I was talking about this Lagrange approach, I said that you can use, when you differentiate them with respect to the equation or their x and y, we can use a simultaneous equation to solve them. So we can use simultaneous equation here. What do we do here? We want to eliminate lambda. Let's eliminate lambda here. We are trying to eliminate lambda. So if we are eliminating lambda, we can say that let's multiply equation 2. This equation. So this is equation 1, 2. This is 4. And this is 5. We are using elimination method. So I want to eliminate the lambda here because there's a common lambda there. Here is x2, x1. I cannot eliminate them. There's lambda here, there's lambda here. I can eliminate lambda by multiplying equation 5 by 2. If you multiply equation 5 by 2, let's do it again. We are going to get minus 4. Well, 2 by 4, 2 is going to give you minus 4x2. Then you multiply the 2 by minus lambda, you are going to get minus lambda 2. And it's equal to 0. So let's call this one equation 6. Equation 6. I'm using eliminated method. I just want to eliminate lambda away again. Now, if we do that, I'm going to add this equation to this equation, equation 4. Add equation 6 to equation 4, because that is where we have lambda, 2 lambda, and 2 lambda. They are all equal. So I want to add them together. So adding them together, I am going to get minus 4 adding them together. Let's add them together and see. Minus 4x 2 minus 2 lambda. I'm adding this one to the equation 4. So plus 2x plus 2x 2x1 plus 2x1 minus 2 lambda and this is equal to 0. So if I do that, you can see that this lambda here is going to cancel. Sorry. Okay. So here, I was supposed to multiply this one by minus 2, right? Yes. Minus 2, sorry. So that this one become positive. Sorry. I was supposed to multiply by minus 2 so that this one become this. Yes. So this one become this. So that we can able to cancel off this. Okay. So this is what we are supposed to get now. So that this one will come and cancel this off. We'll cancel this off. And then we now have our equation here. Left is 4x2 minus 2x1 to be equal to 0. So we can send one across the equal sign, this one across the equal sign. So we have 4x2 to be equal to 2x1. So I want to make x1 the subject. I'll divide here by 2. I'll also divide here by 2. So that this one will cancel this. So that I can have my x1 to be equal to, this one will go here 1, go here 2. It's equal to 2x. It's equal to 2x. So what I can do here is that I want to substitute this equation into, I want to substitute x is equal to 1 into equation x is equal to 2 into equation where we have x and yes, into equation 3. Into other equation 3, that is we differentiated with respect to equation, this equation. Yes, so we can substitute it into this equation. This equation 3. S is equal to so we have x1 is equal to x2. 2x2, yes. So we can substitute this one into equation 3 here. This equation. This equation. Or we can substitute it into this equation. So here we have x and we have x1 and x2. So we can substitute it in any of them to find the value of x or y. Okay. So let's substitute the x there and see what we are going to get. So work the equation 2x1. So the equation is 2x1, 2x1 is it plus 2x1 plus 2x1 plus x2 is equal to 4. So now x1 is given. X1 is given. So let's substitute x1 there. So x1 is given. So we are going to get 2 into bracket x1. X1 is 2x. So we have 2x
2x2
plus, okay, 2x2 bracket close, then plus x2, and this is equal to 4. This is equal to 4. So let me write it here. So we have 2x2 plus x2 to be equal to 4. So if we multiply this one, we are going to get 4x2 plus
S2.
So here is going to give you 5x 2 is equal to 4. So you can make S2 the subject. So x2 is going to give you 4 over 5. And 4 over 5 is the same as 0.8. 0.8. So if you are able to find your x2 to be 0.8, then you can find your x1. Remember that our x1 was equal to our 2x2. So once you have x2, we can substitute our x1 there. And that is going to give you 1.6. 1.6. So we have found the value of x1 and x2. x1 is 1.6 and x2 is 0.8. You can also find the value of lambda. You can find the value of lambda by substituting the
Sir.
the x1 and x2 into the. Yes.
Where do you get a 1 to add
Yes,
to the
go
4 to
ahead.
make 5? So where do you get a 1 to add to the 4 as 1? Substitution. 2 into 2 2 to bracket s2. What is substitute? Hello, sir.
2 into bracket s2.
Yeah. Plus
Uh-huh.
s2
Yes.
is equal to 4. Then where do you get the 1 from to make it
Yes.
5?
The other
Okay. So 2x x2 multiplied by x, the 2 multiplied by x2 is 4x2.
Okay.
It's 4x2. So you add it to the other x2. There was another
That's what-
x2 there. There was another x2 there. So when you multiply this one, you are going to get 4. Then you add it to the
Okay.
the already existing one. You are going to get 5.
Okay. Thank you, sir.
Yes. Yeah. So you can also find the value of lambda. The lambda, you can find any of them. You see here was minus 2x equal to minus 2x minus lambda is equal to 0. So you can find the value of lambda by making lambda the subject here. So lambda is equal to minus 2x x2. And you know the value of x2. You get substitute the value of x2 into the lambda here, and you get the value of lambda. Okay. Okay, so we are able to find this. Okay, so this is get the proof of the whether it is maximum or minimum. Okay, so this, if you want to guess proof that you can guess, once you are able to find the value of x and y, we can be able to substitute them and then find whether it is maximum or minimum. Okay, now I think our time is up. It's 11:10. So please, this is another example. It is your homework. Please, when you go home, use the Lagrange approach, because next time I'm not going to work it for you. Use the Lagrange approach, follow the steps, and solve this one yourself. So next time we are going to meet, this is the solution to it. Even though the solution is there, I encourage you to work it yourself together. But if you work and you don't understand anything, when we come, we'll address it. Then we'll move on to further integration. All right. So
Doc,
if there's no, yes,
Doc, meaning that you are going to send the slides to us any moment from now.
the slides has been sent already.
We have it.
Well, I
You
only
have the
one.
slides already. One thing. Yeah, that is only one. We are still on that one thing.
Okay.
Yes. So we are hoping to finish this one next week so that we can move to the next one.
Okay.
Yes. Yes. Any other concern?
So any free
Okay.
time for the week?
So come again.
Any free time in the week so that you can meet?
Oh, I will let you. I will let the course rep know if I have some free time.
Okay.
All right. The course rep is like she has not been joining, eh?
She's heading there.
Okay.
Oh.
So
I'm
she's not there.
here. See, I'm
We are
here.
all here. We are
Sincerely.
all
We
here.
are all here.
Hey,
Hey, now why you
And it's like, it's not
The,
us. So
the,
the
the ladies, you
noise
don't talk.
at the background, we don't want to talk. Baby.
Azonto course reps.
Ladies, you don't talk.
What?
No, the delegates
Noise
we
from
have
what
here,
background?
they make noise too much. So we don't want to talk. We are here.
Then now that you are not hearing any
Hello.
background.
The mask like
It's dog
graduate.
from. Hello.
Yes, sir.
Dog is left.
Dog is on.
Who is the course rep for e-commerce? Who is the course rep for e-commerce?
It's like Florence or Sue.
But
it
Florence
Florence?
is not here.
Hello,
It's
dog.
Ellen and-
Hello,
Yes.
dog.
It's
Yes.
Florence. It's Florence.
He's gone.
I'm around. Go ahead.
Okay, sir. Sir, you know, I have the book and the question I'd wanted us to solve it, but because you had it's on the
You are ready to solve the question here.
hello, sir. So I wanted us to solve a certain question, sir.
Right now.
And because of lack of time, that's why.
Oh no. I think we have forgotten it. Maybe next time.
Okay, sir.
Or maybe when we finish the network organize like what we did last
For example, like when they write the FOC, what does that mean?
Come again.
FOC. You know, setting up the Lagrange function.
That is first order condition.
First, and then SOC, second order condition. Thank you, sir.
Yeah.
Okay, sir. I have the one Professor
We'll get that.
Professor Bintun used, but all the figures are different here.
I bet it's not the same question.
Hello, sir.
It's not the same question, so you don't expect this question to get. All right, so have a wonderful day. We'll meet another time.
All right, sir. Thank you.
Our course reps, I saw that the mass was beating them, so they just find a place to hide.
Guys,
This one here, it is a
how is the math
random.
going?
Who understood the lesson back so that you take us through. Some of us got confused along the way.
Unless I visit my nose, unless I go revisit my nose, because hey, Jack, this one there is left and right.
This course is after our life.
The Lagrangian is so easy. Even the substitution was even better. Cry.
Or what he started, the substitution was better, but the Lagrangians or whatever,
Lagrangian.
I want to bash my mind. Or by oh, you go be like
small Lagrange.
small Lagrange.
Lagrange yourself. Small Lagrange yourself. Eh? Get out. We go use chainsaw or what? Tape measure. Oh, this one sharpen knife. Then Lagrange yourself. Then get it.
Why you go be?
When
This one, they have to give us.
Eh?
They have to pass all of us.
Small economics, market like this. Small economics.
You see that the Economists one was even better than this one.
This one is good enough small. I upgrade one, abrasive version. This one.
This
so
one is
upgraded.
Senior brother. This one is Economists one senior.
And this one is too much.
Economists one senior brother.
Okay. Let's see this. Next time.
It's doing a pure course.
Hello? Mr. Chubasi?